Shalom. Thank you for joining me today. I'm Andy Jaros, and I'm here to talk about embedded FPGA and assure you that embedded FPGA is really taking off and want you to think about if it's time to get on board. The idea of FPGA has been around for decades now. I remember a guy from TI telling me, hey, we did embedded FPGA 30 years ago, but decided never to actually implement it. So why is it really starting to get traction now? Well, there are a couple of different things for it. The idea of embedded FPGA has been around for decades. I remember an engineer from TI telling me, hey, we designed this and developed this 30 years ago. But yet, when in the marketplace, you don't really see embedded FPGA in many high volume products yet. But so is it really taken off? And is it really getting traction? And why now? And there's a number of reasons for it. One is, Moore's law is flattening. Everybody knows that. So there's only so much performance that you can get out of moving from process node to process node now. And people are starting to throw processor subsystems or accelerators to get that performance. But the problem with hardwired accelerators is once you dedicate it and tape out that chip, that hardware accelerator is kind of, it's frozen, it's static. You can't really change it. And with market conditions changing as quickly as they are, market windows becoming smaller, and you're having to rev up the different versions and updates, you really want those hardware accelerators to be reprogrammable. And the only way to do that is through embedded FPGA. And I think the other key thing is it's readily available off-the-shelf IP now from a number of different companies. You can find embedded FPGA IP available from in TSMC and Global Foundries, even specialty labs like Sandia National Labs, all the way from 180 nanometers down to 7 nanometers. And it's offered by a number of different companies, not only us, Logix, but Achronix, QuickLogic, and Menta as well. So where are people really looking to use embedded FPGA? Well, I can tell you from our experience, it's across the board, from very low power, small amount in IoT, battery powered devices, all the way up to high performance applications for things like 5G for base stations and small cell stations. On the networking side, we're seeing smart NICs wanting to use embedded FPGA as well as for computational storage. And of course, there are the space applications, aerospace and defense, and then general purpose AI acceleration. So it really is being used across multiple market segments in a wide variety of different applications. From our perspective, we're seeing very broad adoption. We've got well over a dozen working chips working in silicon, have taped out, work first time out. We have customers, a number of customers that are in design, well over a dozen, whether they're in fab design or in the beginning of their architectural chip development. And we're starting to see customers doing multiple designs where they've had a good experience with the first design. They like the IP, it's easy to integrate, it's easy to use. Now we're starting to see that expand out into broader portfolio adoption. And our customers are spread throughout the world. So it's not just regionally based. In terms of public companies, you can see the ones on the right, but we're also working with many more that are still under NDA. I mentioned availability and easy to use. From what we can support is as little as 1,000 LUTs up to requirements well over 250 to 300,000 LUTs. Our technology is flexible, so we can support adding BRAM, which is basically scratch pad memory that is attached to the embedded FPGA. We can also support DSP Max for high DSP algorithms. Such as there are some security algorithms or filtering applications. And once we have the technology in an available process node, we can deliver any size array with any of those options, BRAM or DSP options, in a matter of days. So where do we actually see embedded FPGAs being used? Really kind of three different application places. One is just kind of self-evident where people want to integrate an FPGA into their ASIC. So a lot of like in computational storage, a smart NIC, there might be an FPGA sitting right next to the controller. Well, the next natural progression is to integrate that embedded FPGA. You have to do it a little bit intelligently because when you actually look at the design within the embedded FPGA, a lot of that design is static. So you don't really want to put the parts that don't need to be reconfigured in embedded FPGA because that's not an efficient use of area. You want to put those designs in ASIC gates. And then the parts of that design that do change or you do want to program, those are the ones that go into the embedded FPGA. They tend to fall along, control path lines versus data path lines. Data paths tend to stay static, so you want to try and put that part of your design in the ASIC gates. Whereas the control path is where you really want more reprogrammability, and that's where you would use the embedded FPGA. One of the kind of the natural uses of embedded FPGA is sitting on a system bus, be able to do, modify your any protocols, algorithms, security, encryption algorithms, things like that, where maybe you are shipping a chip to different regions and you have to have different security algorithms or communications protocols for the different regions, or you might even have an end customer who has their own proprietary RTL that they don't want to share with the semiconductor manufacturer. And so here's a way to be able to support that customer that they can program the embedded FPGA after you ship that chip to them and it's already in their system. And then the other area is if you have a workload that you need to run, there are certain applications where it just runs better on an FPGA than it does on an embedded processor. So things like if you're doing very wide data processing, if you're doing a lot of DSP activity, then it really is more efficient running it on FPGA. And even though it may take up more area than embedded processor, we've done app notes and studies where we can show that it actually consumes less power, even though the area might be a little bit bigger. In terms of availability, Logix has the IP available in a wide variety of process nodes from TSMC and Global Foundries. You can see we're silicon proven in 28, 16, 12, GF12, and Sandia's proprietary process, and then we'll have the small core available in TSMC here at 40 this summer. The way we do our approach is that we create a GDS that is compatible with multiple variants of a particular process. So our GDS in 28 HPC Plus, for example, will work in 28 HPC and 22 ULP. Likewise with TSMC 16, that's compatible with 12 FFC and 12 FFC Plus. In TSMC 7, we'll also be able to support TSMC 6 nanometer. It does take us about 6 to 8 months to do a port, but like I said before, once we do a port, we can build up any size array by connecting these cores together and deliver that array within a matter of days. Ease of use is also very important. When you get embedded FPGA IP from Logix, you get what you would expect for standard hard macro deliverables. We give you a .lef, .lib, GDS, encrypted Verilog netlist, SPICE netlist, test vectors, RAM. We have a wrapper to connect to the programming port to AXI, AHB, or JTAG. And then we provide support as well. So we want to make sure that our customers have a good success on their initial project as they get familiar with our technology. One example I like to highlight is the shortest time that we had a customer tape out from shipping our deliverables to their tape out was 2.5 months. And the chip worked out first time out. Because we take a standard cell design methodology approach, we have a lot of flexibility when we implement our technology and target different process nodes or different applications. In particular, for customers who are looking at high volume or doing multiple chips, they may need some special features like power management. They may be targeting high reliability applications, or they may want to just reduce have the minimum size of the embedded FPGA core itself as a base to work with. All of those things can be addressed with our methodology. Of course, there's always going to be a schedule and a cost impact of it, so it's cheaper to use what's available off the shelf, but those capabilities are available within our technology. An example is our power management that we've implemented in our small EFLX 1K core in TSMC 40. Basically, it implements a sleep mode. that allows you to shut off the power to the logic, DSP, and interconnect switches. What that does is it enables the power to the configuration circuitry to stay active. Thereby, you retain the design within the embedded FPGA, even though the bulk of the gates are power gated off. This is in addition to the inherent clock gating that our software tools insert into the design, into the fabric. So at a very high level, you got clock gating. That's part of all of our products and part of our software. We can implement the power gating here. And then there are other options that we can do, such as, we call dual power rail, where we pull the power gating outside of the EFLX core, helps reduce the area of the core a little bit, and helps you leverage whatever power gating control mechanisms you have within the ASIC itself versus duplicating it within the EFLX core. We can support different VTs, so if you need more performance, we can use SVT or LVT for the logic and DSP connect switches. Here we're showing in the low power, we're using UHVT for absolute lowest power applications. And we can support body back biasing. There are certain applications such as space, autonomous vehicles, and medical that require high reliability. And there's a number of ways that we can support that. Out of the box, if you use Synopsys Simplify for synthesis, Premier version does support triple redundancy of the logic, including the voting logic. So you can actually take what we have available off the shelf today and implement triple redundancy for any automotive application and get going right away. The next level of reliability is we have done ports where we've used rad hard standard cells provided by our customers. We use those in all the critical circuitry, that including configuration bit cells that might be susceptible to single event upsets, with a rad hard by design embedded FPGA IP that can be used in any ASIC. And then going one step further beyond that, we can implement triple redundancy of the bit cells in flip-flops. And if you want the smallest rad hard by design, we can work with our customers for them to provide a rad hard by design bit cell that we can implement within the embedded FPGA as well. In terms of cost reduction, there are a number of different ways. First, out of the box, the standard product is designed so that you only put in an array size for the amount of embedded FPGA that you really need in the core. So really, it's kind of modular and optimized that way so that you don't waste a lot of area for unnecessary or unused LUTs that your designs won't use. We also have different licensing models available. So if you are planning a product portfolio, and we can provide a multi-use license or a term license, and that effectively lowers your average cost per chip tape out. And then going into area reductions of the embedded FPGA, there are a number of different things that we can do. We can look at optimizing the core for small arrays to make the area a little bit smaller. We can look at using additional layers of metal as well that would have an impact on an area. There are certain applications, particularly in networking, where you may want to connect a lot of wide buses to the embedded FPGA. Sometimes that requires a very large array just to be able to get the number of IOs. Well, we have the ability to change the ratio of the IOs to LUTs, so we can develop a very high IO count EFLX core, which effectively would minimize the number of cores you would need in an array for those high IO type of applications. Typically, you see those, again, when you see many wide buses connecting into the embedded FPGA to do some kind of control or muxing functions. And then beyond that, we can actually reduce area by implementing full custom design techniques for different parts of the embedded FPGA blocks that we build. So there is a way to be able to customize that and actually get into a smaller core as well. Of course, the hardware IP isn't very usable without software tools. We have a full suite of tools. For synthesis, we use Synopsys Simplify or Yosis for those applications needing super low cost. We have our own eFLX compiler that does the place and route and bitstream generation. And you can kind of see a couple of different screenshots of the GUI that we've developed over the years for our compiler. It's very easy to use. It allows you to see the placement of the design. You can drill down and take a look at the where all the nets are connected. You can take a look at the power across different process corners. So and what that helps do is build confidence that the design, once it's programmed into your chip, is going to run at the speeds that you predicted with our software tools. So our correlation between our software timing that you see in the EFLX compiler and silicon timing is usually within a couple of percent. And then we have tools associated with that are available to help with debugging of your design as well. And then if you are a true skeptic and you want to see that design running in silicon, and we do have evaluation boards available in TSMC 12, 16, GF12, and 28. So you can actually run it, make sure it actually works well before you even sign a license agreement. And then to help you along the way, we've got a bunch of different app notes and white papers, all from taking a look at, how would you use an FPGA in your SoC to actually helping you implement and getting best practices out of the embedded FPGA once it's already in there. So we've got lots of benchmarking data, we've got application data and suggestions and guides to help you along the way. And then also available are demos. So we have a microcontroller subsystem demo where we have an ARM M0 based subsystem. And basically we expose an HB and an AXI bus, and you can actually program in whatever hardware accelerator you want, attach it to the microcontroller subsystem, do some software development, and kind of test out your accelerator in an MCU type of environment. Taking a step beyond that, if you're looking at applications where you want to be able to swap in and out different FPGA IP blocks, we have a way to be able to do that. We call that modular FPGA. So it's basically an infrastructure that allows you to support containerized IP blocks and be able to program them very efficiently into the embedded FPGA. And then our latest demo is one where we're actually showing the EFLX core running a binary neural network model. So it's kind of hard to see here, but we have basically a digitized image scrolling up the screen. Then underneath this, you can't really see it, but here is where the neural network model is identifying what that digit is. What's kind of neat about this one, it's running on our evaluation board, and you can see the lights toggling corresponding to the number that's being identified. But what's really cool about it is it only takes up about 200 LUTs. So this fits in our smallest EFLX 1K core, does some basic neural network acceleration. So that is available, can be shown today. And with that, I think that kind of wraps up my slides. So now I'd like to open it up for questions.